喂，刘老师。
OK，紧张你好。
哎，
对，OK，
哦，我好像没有这个权限，现
，OK，
在。
行，
嗯，
啊啊，
我调。
我需要make you a co-host，
嗯。
稍微等一下，他们一般会我们是
啊，不着急，不着急，没事，我就想
啊，
我来稍微看一下没那个共享啊什么的有没有
对，
问题。
通常是我们是10点开始，然后通常来说他们会10点过5分，你也
好的，好的，没问题。
，OK，
嗯，
嗯，因为有些课是10点结束，
明白。我
对，
这个 talk 其实是还没讲过，这才做的 PPT，
没问
看一看。
题。
嗯嗯，我看一下摄像，然后
哦，OK，我们现在说话那个 audience 可以听到，所以说我们现在 switch 到英文可以吗？
OK，no problem。
Okay. Yeah. Okay. Yeah. Yeah. Let's try your PowerPoint.
Yeah, let me see. Full screen share. Okay, so does it look okay? Can you see the screen?
I can see. Yes. Thank you
Okay.
so much. I can see the screen. Yeah.
Okay,
And
cool.
let's aim at starting at 5 past 10
Yeah,
because
no worry.
a portion of students will have class from 9 to 10 o'clock.
Okay, sure.
And yeah, how is everything going?
It's been good. Yeah. So the
Mhm.
semester started this week, but yeah.
Oh, the semester starting this week. This week. Okay.
Yeah,
Oh,
yeah. Yeah.
we are
What about
already yeah,
you?
we are already halfway into our second semester.
Oh, really? Cause there's no spring festival. Right.
There is a 2 day spring festival.
Oh, okay.
Our semester start on 2nd of January
I
and
see.
something like beginning of May.
Ah, okay. So it ends early. Yeah. Okay.
That's
So you
early.
have a very long summer.
Not quite. Our so-called first semester start early as well. It's like beginning of August.
Ah, okay.
Yeah.
Okay. So do you have a longer semester? So how many weeks are there?
Uh, uh, um, I I think it's something like a 16 teaching week for us,
Okay.
but the students have one or two reading week, and they
Uh,
have exam week without teaching. So their semester is a bit longer than ours. Yeah.
okay. Okay. Makes sense. Yeah. I think then it's the same in Beijing and in Singapore. Yeah.
Yeah. So how many years have you been in Tsinghua now?
Uh, Almost 3 years. So
Oh,
I'm yeah, yeah.
yeah. Well, so you joined roughly during the time of the large language model evolution, and yeah.
Right.
Yeah. So how much
Yeah.
have you changed your research your research like plan because of large language model?
Yeah, so actually I didn't study any statistical learning in my PhD. So my PhD was all about optimization.
Oh, wow, wow.
Yeah.
Yeah,
Yeah, but some
yeah, go ahead, yeah.
yeah, but somehow it hits so my PhD thesis is on understanding optimization for neural networks.
Yeah.
But yeah, there was very little progress actually. I think over the years compared to other fields.
Oh, I see, I see.
Yeah, our understanding so we are still using Atom, right? So
Yeah, yeah.
which is like 10 years ago. So there's little progress. So I was thinking maybe we should use tools from other fields. So that's why I spent several years on statistical learning to see if we can do something. Uh,
So,
yeah.
how do you think about? So I'm relatively unfamiliar with statistics learning part, and what's the progress in the whole field at the moment?
So so basically that will be I will have a quick summary about that in this talk. But I think people are starting to think about so statistical learning originally is about supervised learning. It's about you train on some train data and then how does it perform on some idea validation data. But that clearly does not fit in the current paradigm of large language models, right? Where the training and testing are completely different.
That's right.
And yeah, so there are many efforts to understand what is going on, and I think if you are interested, I would recommend some like workshops in Simon's Institute. So I think they have a very good summary of the community.
Oh, workshop in which institute?
Simon's, so the at Berkeley. Yeah.
Okay, 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 yeah. Yeah.
Yeah. But anyway, so I don't but yeah, I think I've seen optimization. The theory is still a little bit left, not a little bit, it's significantly left behind by the experiments. Yeah, I think the current situation is still we are trying to understand what is going on, rather than to make some predictive hypothesis.
Oh, I see, I see.
Yeah.
Yeah. And how is so I'm curious, how do you organize your team at the moment at Tsinghua? So is that everyone work on statistical learning on large language model, or is like a more
Uh,
diverse within the team?
Actually, so these works are not done by my PhD students. Um, Yeah. So for every students, I would recommend some of the topics, and they are very diverse, and so they pick their own for in because I'm not very good at management,
Yeah.
so I let them manage themselves. So it's I'm very, very much hands off. So I think I'm an exception. Not That's not the usual situation.
This is actually very similar in my other previous lab I was in, and
Mm.
I'm not sure if you know that I was in CCL for 2 years. I
Yeah,
was
yeah, you told
in
me.
machine learning for biology lab, and then I moved to across the river to Harvard Medical School. Then I moved to Shop Angels lab. I think in all the lab I was in, the PIs are relatively um, hands off. I mean, actually, they're extremely hands off. So I'm just curious as a new PIs like us, how
Hmm.
hands off should we be? Oh, by the way, by the way, John Scarlett is here. Who is co-hosting this? John, can you hear us?
Hi, hi, Jingjia. Thanks for being here.
Hi, Johnson. Nice to meet you.
Yeah, John is an associate professor in computer science here in US. He has gained quite some reputation in his field of research in machine learning and computing. Yeah, and
Just
then
like partly machine learning, yeah, information theory, machine learning, statistics, like a
I
bit of a
see.
mix. I'm not doing the really popular, deep learning LLMs and so on.
Okay. Yeah, I'm also new to this field actually. Yeah, I was
Okay.
talking to Diego about this. Yeah.
yeah. So for large language model part, our team we have relatively only a small portion, roughly one third of the students working on large language models.
Hmm.
Some people work on something similar to reinforcement learning or community feedback because
Hmm.
in my previous line we work on something called deep net, and
Hmm.
which is similar to reinforcement learning. So we use that on large language model, and some people working on agents that
Hmm.
more to solve specific problems in biomedical field, like a
I
very
see.
concrete problem. How do you make this diagnosis meaningful and use that to inform the decision by the doctors, those kind of things. So
Okay.
and um,
So sorry, do you mean your group or your department?
my group is my group.
Oh
Yeah.
wow. So it sounds like a very large group. It's like a
No,
diverse. Yeah.
not,
No.
not quite. I mean, it's like it's not a very large group, but different people are working in different direction. That's a
I see.
problem.
I see.
Yeah, yeah.
Okay.
Yeah, then quite a few people are working on tokenization. So I have been working on this direction for 5 years now. Tokenization.
Tokenization for image or for text?
Okay, for usually for non-text data modality, but
Oh, I
we
see.
also work on text. Yeah. For example, DNA is like it's already discrete,
Okay.
oh,
I
but
see.
long to solve, right? But we're also working on that. So
Hmm.
that's a major focus in my team. And we
Okay.
see tokenization, how to make it efficient, how to make it reliable.
I see. So are they are they designed similar like text where you just use some like information theory criteria to group the tokens, or in they will be different for
So
DNA, for example.
So for DNA, the project are still at its early stage. The
Mhm.
problem we want to solve is DNA sequences are too long for language models to deal with, like a
Okay.
billion total
Uh,
level. Right? How do we
uh-huh.
do in an effective way?
Mhm.
For images or waveform information, such as those like a continuous data modality, we
Mhm.
are working on how to discretize them so they can
Mhm.
be converted into discrete token
Mhm.
properly for mostly for generative models. That's what we do. That is actually our major focus. Yeah.
I see. I see. Yeah,
Um,
I remember that from your talk. Yes.
I think we might be good to get started. It's yeah.
Yes,
So
yes. So I think we can get started. Let me give a introduction to Jinzhao. So Jinzhao is an assistant professor in Tsinghua IIS. So another name for IIS is Jinzhao class. And he graduated a few years ago from MIT ECS and under supervision of Ali Jabal Bey and Suresh Sara. His research focused on proof theoretical analysis on practical large-scale algorithms. He now aims to propose theory that are simple and can predict experimental observations. Jinzhao is also interested in machine learning application, including dynamic system formulations and so on. He received the Ernst Gilman Thesis Award and George Sparrow PhD Thesis Award. Um, that's introduction to Jinzhao. And so for people in the attendees, I enabled the question and the answering tab. If you have a question, you can post there, or you can raise your hand, click the raise your hand button. Then I can find an appropriate time. I can allow you to talk. And yeah, I think we can get started. Thank you so much.
Okay. Thank you, Dianbo, for the introduction and for the invitation. So today's talk is about understanding LLMs with statistical learning. So this is some of the recent works that I did. So this is and it's the first time I give this talk. So if there's anything that is confusing or unclear, so feel free, Dianbo, please just interrupt me at any time. So it's no problem. And so these are the references, and I would like to first thank my collaborators. So this talk is based on three works. So the first work is with Peng Kun. So Peng Kun is an assistant professor at Tsinghua Stats Department. And second work is with Kaiyue and Huaqing and Hongzhou. So Kaiyue and Huaqing are undergrads in your class, and Kaiyue graduated. And Hongzhou is my friend from MIT, and he is now at Amazon. And the third work is in collaboration with PhD students Amir from UCSD and Professor Michal Belkin from UCSD. Okay, so these are the references. And so this talk is about LLMs and statistical learning. So before we go directly into the works, so I will have a very quick discussion about what is going on with statistical learning and LLMs. Okay. So just a quick, I think this is maybe around the first course in machine learning, one would learn this. So the idea of statistical learning is that we, from a population distribution, we sample some IID training data, and then from this data we can use a learning algorithm to learn from a class of functions and to get a predictor f hat. Okay, and then after this, we would like to see how the model perform on the test distribution, where the test distribution is approximated by the training data, but it's not exactly the same. Okay, so this is the standard framework, and so without diving into the theory, but the key takeaway is this figure which we often see. So it says that the excess risk, which is the test performance, can be decomposed into two parts. So the first part is training error, and it makes sense that training error is smaller if the model size is larger because we have more expressivity. Okay, and the other part is called uniform convergence error, which is actually related to the generalization gap. So the larger the model, then the larger the uniform convergence error. And so this perspective is very fundamental to statistical learning, and it leads to important techniques that we still use today. So for example, it says we should always use a validation set. We should not just trust the training set performance. We take that for granted today. Right. Another is regularization. So it says, okay, so whatever you do, you should think about how to regularize the training and the model so as to get better performance. Okay, so these are classical results. It's very important. But I think back in 10 years ago, so we realized that this view has a problem for deep learning. So this is the first challenge. So deep learning poses challenge for statistical learning in the following ways. So this is a well-known paper called Understanding Deep Learning Require Rethinking Generalization. It says, okay, so the previous theorem says the larger the model, the worse the the generalization gap. Okay. But this one is saying, okay, so if so I can confirm by training the model over data with random labels, and we can see that the model can still fit the data. Then from the uniform convergence theorem perspective, this means that the gap should always remain large because the model is large enough to fit anything. Okay. And however, we can see we know from empirical evidence. So I just pick a plot from a paper, but we I think everyone knows this. That usually, for example, if I want to train an image classification model over some Cepher data set, probably with larger model we can get better performance. So we don't see the trade-off between model size and validation performance here for deep learning. Okay, so this was the first challenge we saw several years ago, and there are many ideas to explain why this happens. Okay, so I list several ideas, but I don't have a very detailed related work. So some ideas are called implicit bias, some are called stability, some are called backpropagation view. And I think they are all similar in the sense that they exploit the condition that although the model can train from a large class of predictors, but after training, because of the bias in the algorithm and the bias in the data, somehow it always learns the good model, not any model. Okay, so as an example, so for example, if we want to classify these two clusters of data, so one can prove in this work that if you train a gradient descent, if you train a linear classifier with gradient descent, then it always converge to the max margin solution. Okay. And usually in statistical learning, people will assume max margin implies some good generalization. All right, so these are all good. So if you have any questions, you can stop me. Um, so this I think these are very intuitive and very novel ideas in explaining what is going on. But when we actually go into non-parametric models or nonlinear models, it is hard to quantify what is a good solution. Okay, so for example, so people may think that a large margin is a good solution, but if we look at this plot on the left, okay, so we consider so there are two features. Okay, so one is x-axis, the other is y-axis, and we want to classify the blue points from the red points. Then the large margin solution will look like this, like a zigzag, right? But a simple solution may be just a linear predictor. So for a nonlinear model, it's unclear what is simple and what is good. Large margin solution may be very complicated, okay? And simple solutions might have violations, right? So for example, here, if I use a simple solution, then it cannot interpret the data. So therefore, so quantifying what is a good model, even under these implicit bias and stability perspective for nonlinear models is very difficult, okay? And so I think that was so all these were before the trend or the rise of LLMs, and we were already have a lot of debate on what is going on with supervised learning. Why does over-parameterization help? Okay, so but today we will talk about a new challenge, which is understanding what is going on with LLMs. Okay, so I think this is what I would say a second wave of challenge for statistical learning. So this is what a LLM is typically do. Okay, so LLMs are trained on next token prediction on some random website data. Okay, so it gives a prefix for a sentence, and the model is trained to output the next token, the next word from this sentence. And somehow, very interestingly, so this seems to be a random task, and with very large model with billions or even trillions number of parameters. And but the model generalizes very well. So this is called a scaling law, which we will spend more time to talk about. But the idea is that okay, so this curve, this slope is significant that we can afford to scale up the model and get better performance. Okay, so I think this is the first question. So when we train a random task with a very large model, uh, why is the scaling so benign that the error converges very fast? Okay, so this is the first question. And the second question is, although large language models are trained on next token prediction, but in practice, we don't really evaluate them on next token prediction because we don't care about next tokens, right? So what people do is, for example, in DeepSeek tech report so people evaluate large language models on various different data sets. So for example, MMLU is I think a uh, test college level tests, and GPQA, math, and ME are math tests, and Codeforce and SWE are coding tasks. So these tasks are all very different from where the model is trained. Of course, there's a gap from using the model from pre-train to deploying them to evaluation. There's a post-training phase, but even without the post-training, the model performs uh, non-trivially good on these tasks. Okay, so that's the second. Okay, so here I just give a random example from Amy, and one might imagine that this kind of question and solution would not be part of the training, would not align with the distribution of the training data. Okay. Okay, so if we view LLMs from the statistical learning perspective, so I think the first there are two questions. So the first is what we discussed. So why does the scaling law exist and why is it so fast? And the second is, so what does generalization really mean if we move out of the supervised learning setup? Okay, so if the training task and the test task are very different, so why can we get generalization and what is generalization? Okay, so these are the questions that we would like to discuss today. Okay, so of course I don't have the answer, but we have some kind of explanations and the theory for this. And so this is the plan for today. So given the previous questions, we will talk about three projects, which corresponds to the three references. Okay, so we will start with the first one. So we'll talk about scaling laws for non-parametric models. Okay. Let me see the time. Sorry. Okay, so first, what is the scaling law? So I think scaling law was the most popular word 2 years ago. It is not so much today. Okay. Uh, so a scaling law says that if I train, so each curve here is the training trajectory of a language model. And the color of the curve corresponds to the size of the model. Okay, so the number of parameter in the model. And the x-axis corresponds to the training steps. And we can see that for a fixed model, if we train longer, then the error decays, right? So that makes sense. But the most interesting is, so if we plot the training curve for all the models, and we select the optimal training step for each model, and then we somehow get a linear plot in this log-log plot. We got a linear line in this log-log plot, and the exponent is negative, somewhere around negative 0.05. Okay, and negative 0.05 is not very fast, but it's also not very slow compared to what we can compute today. Okay. So based on this, so we have two questions, as I said before. So why is the exponent such a strange number? Okay. And so if one is familiar with statistical learning, so this kind of rate hardly happens because it's neither parametric rate nor non-parametric rate. Okay. And so and then I would raise another question. So this is a scaling law with respect to the computation. So what is the scaling law with respect to the dataset size? And so we will start from the second question because we can find that answer in their original paper. Okay. I think I listed the paper. Sorry. I forgot to include the reference. But I think I have the reference later. Okay, so this is the reference. Okay, so we can find the scaling law with respect to data sets in their paper. And so they have two plots. Okay, so on the left-hand side, it says, okay, so if I fix the data path, how does different models, so the color always corresponds to the models. So how does different model perform as I increase the number of tokens, the number of samples? Okay, but in practice, we know that if the data set size is larger, probably we need to train more epoch in order to memorize all the data. And therefore, so there's another plot that says, okay, so if according to the scaling law, I predict the optimal number of passes over the data, so which means I train long enough so that the models can memorize the data, then how does the model perform for various data set size? Okay. And I want to highlight this red plot. I think it's more informative and more interesting. So we can see that if I increase the data set size, so unlike the previous plots where the rate is linear, here the rate is fast at first and slow down later. Okay. So it means there might even, so it means scaling up the data set might not be the solution to solve all the problems because somehow the error decay would saturate. Okay. So so according to their paper, so they also quantify so the rates. Okay, so this is the rates, and they say, okay, so we have some fractional rates, but also somehow the rates slow down. Okay, so this is the question we want to answer. So can we use statistical learning to understand why this happen or when this will happen? Okay.
Just quickly, does it
Yeah.
matter which loss you're looking at? Like, or is this observed over a variety of different losses?
Okay. So this plot is on the next token prediction loss. So this is the same. This is the same loss as the training loss, but on a validation set.
Okay,
Okay.
like is
So
it like a log log
yeah, like a
loss?
cross entropy, basically
Cross
cross
entropy?
entropy.
Yeah. Okay.
Yeah. Okay. Um. Okay. Cool. So this is our first question. So can we use statistical learning to understand why this is going on, so this matters a few years ago because we usually people would think, okay, so scaling up is a solution, but so at that point we want to say, okay, so even though it's scaling fast at the beginning, it doesn't say anything about what happens later. Okay, so this was 2 years ago. Okay, but anyway, so let me give a quick summary about what we know from canonical statistical learning. So canonical statistical learning usually have two kinds of rates. One is called parametric rate, where we assume that the function class is limited, and the function class complexity can be bounded by p. So p is like the parameter count or like a VC dimension, for example. And then usually one get two types of rates. One is 1 over square root n, the other is 1 over n. And another is called non-parametric rate, where we don't bound the parameter size, but because the parameter size can be even much larger than the data size. And then usually for this kind of learning algorithm, one would get this kind of rate. And here, the D is the data dimension. Sorry, I don't have that here. But D is the data dimension. So this is what people call the curse of dimensionality, which means to learn these problems, you need exponentially more data compared to the data dimension in order to figure out the ground truth. So this kind of risk cannot explain what is going on. So I want to highlight two things. So first is, so our exponent is somewhere between 1 over 2 and 1 over d. Okay. And the other thing is the rate is varying across n. So we don't have a uniform rate for different choice of n. Okay, so the convergence rate is not the same for all choice of n. So can we understand what is going on? And so to understand this, we propose a simpler model. Okay, so that's what we could do. So in order to do the theory analysis, we simplify the problem. And so basically, we want to see what, okay, so let's consider a simple non-parametric and nonlinear model nearest neighbor problems. So Kn means K nearest neighbor. Okay, so for K nearest neighbor, what will happen? Okay, can we observe the same behavior? And actually we can. So this plot is training nearest neighbor on two very simple data sets, MNIST and FMNIST. Okay. And we can see that for these two data sets, So for MNIST, it's a very simple data set, and the scaling always look very good, right? So the test error decrease fast. Okay, but for FMNIST, we see the same behavior where initially it's fast, but later it slows down. Okay. And so we want to understand why this happens. So our first intuition is coming from that. So this experiment suggests that what's important is how the data distributes. Okay, so because FMNIST is, we know, a harder data set compared to MNIST, then therefore we need to model the complexity of data distribution into the prediction. Okay, so this is missing from previous statistical learning results. So the question is, so what is the simple data and what is hard data? And intuitively, one could think about this case. Okay, so if I have data distributes over the hypercube, then the left one should be easy because it can be separated by a linear classifier. And the right one is hard because somehow you need to query every vertex, which is exponential in D, in order to figure out what the ground truths look like. Okay. So this is the intuition, but actually it's not really straightforward how this can translate into a theory. Okay, so we give a simple experiment here. Okay, so here we do even simpler experiments compared to MNIST. So we use synthetic data distribution. Okay, so here, so the first one we simply assume the data follows a Gaussian distribution. Okay, and then the optimal decision boundary is just the unit vector. Sorry, the basis vector. And then if we train a k-nearest neighbor with different data dimension D, and we can see that the scaling law on the log curve, on the log-log plot have the same slope. Okay, so having the same slope means that the exponent on their n is the same. Okay, and therefore, so they all follows the parametric rate. This is good. Okay, but if we change the data distribution a little bit, so that it does, so the data distribution is no longer Gaussian, is uniform over a hypercube. And we also have a linear boundary that look like this. Okay. And then what happens is, even though this distribution is supposed to be simple, we see that if we really train a nearest neighbor classifier, then the rates will slow down for large dimension. Okay, so this slope change on log-log plot, this is log-log plot, and the slope change means the exponent changes. Okay, so this means that simply saying that the decision boundary is simple is not a accurate description on the complexity of data distribution. Okay, so we take a few more steps into this. So I'm not sure how many audience are from a theory background, so I might go a little bit fast because I think this might not be very interesting. But I will slow down at the conclusion. Okay, so basically, we show that, okay, so the decision boundary cannot describe the data complexity. So what can describe the data complexity? And later we found that, okay, so this can be characterized accurately for nearest neighbors because for nearest neighbors, we know exactly how the boundary look like given the data. And the idea is, if we have a data that distributes uniformly over this rectangle, okay, and let's assume the optimal decision boundary look like this, then the idea is if we look at any points in this black rectangle, okay, in this sub area, then these points are easy to learn. And that is because if I plot the radial density function at point X, then the data from the same class always dominates the data from the other class. However, if I think about another point here, okay, so another point X prime here, and similarly, I plot the radial density function, then I know that the correct label dominates the opposite label only for very small radius r. Okay. So, and in high dimension, if I want to find signal in this very small radius r, it will require exponentially many samples. Okay, so that's basically the intuition. So with this, we can characterize what is a simple distribution and what is a hard distribution for nearest neighbors. Okay, and we can derive a theorem out of this framework. And the interesting thing is, okay, so if we apply this framework to this very simple example, this example in statistical learning is called logistic regression with normal design. It's still an active research area. somehow because, for example, linear regression is still an active research area for statistical learning. But anyway, so if we apply that framework to this example, and then we can show that so nearest neighbor classifier can achieve this rate. And so this rate is known to be statistically optimal. Okay. And so why is this interesting? Is because usually people would solve this problem with linear regression and show that it's achieve optimal rate. But nearest neighbor is a non-parametric model. It has no idea about what the ground truth is, whether it's a simple model or whether it's a simple data distribution. Even though it's agnostic to that, it can still achieve the optimal rate. So up to our knowledge, this is the first parametric rate for nearest neighbors. Okay. And similarly, I think another interesting result is we can also show that if we apply the framework to this model, then two-phase rates would appear. So where in the first rate is polynomial convergence, and in the second rate it will suffer from curse of dimensionality, where exponentially more samples is required. Okay, and so this is the upper bound. Actually, in our paper, we also have a lower bound that says, okay, this slowdown is unavoidable. Okay, so this is our journey for nearest neighbor classifiers. And if we were to summarize what we did here, basically previous statistical learning usually can fall into two categories. So one is uniform convergence, which doesn't assume anything about the data and the algorithm, but assume that the function class to be learned from has bounded complexity. Okay, and later, after the challenge of deep learning, there's Pack-Bayesian-like analysis, where they don't really assume anything about the data and the model, but they assume that whatever is learned by the algorithm has bounded complexity. Okay, so here in our analysis, we highlight the importance of data distribution. So in addition to thinking about the algorithm and the model, we should somehow we should somehow characterize how the data distributes. And if the data has bounded complexity, then the model can learn fast. Okay, I think this perspective or this analysis is missing from previous ones. Okay, and another takeaway, I didn't put it here because I think now people know that you cannot solve everything by scaling up the pre-training. Okay, so because even though it's fast at the beginning, it's not correlated with what happens later. Okay, so that's the first part of the talk, and so basically we talk about scaling laws for non-parametric models, but it has nothing to do with LLMs. Okay. Okay, so the question is, so we can characterize what is the simple distribution for nearest neighbor. Okay, but we don't really care about nearest neighbor. So what is the simple distribution for LLMs? Can we extend the analysis? Okay. And so that's our second project, which we want to understand the learnability of next token prediction. Okay. Okay, so this is a transition. Okay, so we said for KNs, we know what does it mean for data to distribute benignly, but what is a benign condition for large language models? So before we talk about that, we will take a brief detour to talk about what is a chain of thought for large language models. Okay. So maybe people already know this, so let me, but just let me quickly recall. So large language models is a next token prediction model. Therefore, you can give it a question and ask it to answer the question, which is the future tokens, right? But in early age, LLMs really struggle to answer this question. So for example, so this question ask what is the first letters of Elon Musk, and then sorry, the last letters, and then you need to somehow you need some thinking process, okay, to figure out. And therefore, in I think 2022, yeah, in 2022, this OpenAI found that okay, so although the model cannot answer this problem directly, it can answer this correctly if it were allowed to output some intermediate steps. Okay, if it were asked to think about this carefully before giving an answer, and then it will output intermediate steps and give the correct answer. Okay, so this is called chain of thought. So initially, I think this is quite heuristic, right? It's like neuroscience. It's not math or computer science. So or it's cognitive science. Okay, so should we understand LLMs by thinking about how human behave? So that's not my expertise. But actually later from a second thought, it really makes sense even if you think from the computer science perspective. Okay, so why? Um, so when I first studied deep learning, like the classical results would be about expressivity, optimization, and generalization. Okay, and the most classical result from expressivity is saying is this 1992 a result. It says, okay, so if the neural network is wide enough, it can approximate any smooth function. Okay, so this is a classical result. And but if we think from this perspective, it's very hard to tell why do we need a deep neural network compared to shallow network. Okay, so there are some more recent works on this. It says, okay, deep network cannot be efficiently approximated by shallow networks. But again, so they have their own. So these results are good, but they also have their own limitations. But I want to propose a different idea that after transformers show up, that people start to think about expressivity in a different way. Okay, so previously we want neural networks to approximate smooth functions. Okay, but recently people think, okay, so why maybe we should not approximate smooth functions. We can ask neural networks to approximate a program. Okay, so if we think about what program can be approximated by transformers, uh, then it's closely related to the length of the chain of thought. Okay, so if a finite depth, finite size transformer can compute chain of thought of size n, then it means the program that it can approximate can be uh, upper and lower bounded by time complexity Tn and space complexity Tn. Okay, and it makes sense because if you think, so if I have a finite transformer and I'm asked to give the answer, then and I'm asked to give the answer directly, then the most amount of computation I do is just to run an inference, right? But if I'm allowed to do to use a COT, then it means I can use more computation before giving the answer. Okay, so this is very straightforward. Okay. I think this is this is a very simple idea, but it can lead to very interesting observations. So, for example, I think there was a time that people figure out that LLMs, although they can answer complicated questions, but they can not do multiplication correctly, right? So then there are many works that tries to do multiplication with LLMs and see what is the limit. But if you think from a theory perspective, in this work, one can show that LLM of finite size can never do multiplication correctly for large numbers. Okay, and so the idea is from a computer science theory perspective, where you show that okay, LLM can be approximated by constant depth circuits, but multiplication cannot. Okay, and so this is, I think, a very interesting observation from thinking about approximating programs. Okay, okay, so we took a detour to talk about chain of thought, and the current existing analysis says, okay, chain of thought would help increase the computation for LLMs. Um, but in practice, I think when we talk to LLMs, the task we require is not that difficult, right? If we just ask it to do very easy computation or to compare the value for two numbers, right? So it doesn't require a lot of computation, but sometimes language models still fail. Okay. And so in this second project, we want to understand why that happens. And our main idea is that the previous result is about expressivity. It's not about learnability, which means the language model have the computation power to do the task, but during pre-training, it didn't learn to do this. Okay, so our message is computation does not imply learnability. Okay, so let's see how we approach this question. Okay, so we would think about, again, we simplify the model. So because we cannot talk about the distribution of natural language, that's too hard. So we use simpler sequences. We think about learning with parity examples. Okay, so let me briefly talk about. So what is a parity example? Parity is a function map that's given an input of size d. Okay, so here d equals 5. We have 5 inputs. It computes the exclusive OR of several secret digits. Okay, so here it computes the exclusive OR of digits 1, 2, and 4. And you can pull out the first digit 0, second is 1, and 4 is 1. And then I do an XOR and I get answer 0. Okay, so this is a parity. So parity clearly is parameterized by the index for the secrets. And so here we talked about COT, and I want to highlight, so there are two ways to present the sequence. One is to give the input and to tell you this is the end of the input and to give you the answer. Okay. And the other way is to give you the input, tell you this is the end of the question, and then give you the intermediate computation step. Okay, computation step is okay, so first secret and the second B1 XOR B2, and then last B1 XOR B2 XOR B4. Okay, so this is the COT sequence. And then we would ask, okay, so given many such sequences, can a transformer learn to predict the answer? So this is a very typical next token prediction problem. So one can think about it as a very typical next token prediction problem. So can the transformer correctly learn the distribution? And and we did an experiment here. Okay, so here the color corresponds to the sample complexity. So the smaller the lighter the color, the better the complexity. Okay, and the first row corresponds to sequences with chain of thought, and the second row corresponds to sequences without chain of thought. And we vary the number of layers and heads and other parameters. And we can see that with chain of thought, the sample complexity remains low. Okay, so this is log plot, and the sample complexity remains relatively low, but without chain of thought, the sample complexity is exponentially large. Okay, so we want to verify. So if we look at from a different axis, so how does the sample complexity scale with the problem size? So if we fix the number of digits to be 30, and we change the number of secrets, so we can see that with COT, the sample complexity remains relatively almost a constant, but without COT, it's exponentially growing in K. Okay, so we want to ask, so why does COT, why does chain of thought not only help with computation, but also help with learnability? And so our first hint is that we show that this is not due to expressivity. Okay, so even with one layer transformer, we can express parity with a one layer we can express the parity function of arbitrary index k. Okay, and so this is our theory. We basically construct such a transformer, and then we prove that. Okay, so I gave the result first, and then talk about how we prove it. We prove that if you use COT, then a transformer can probably learn parity problem with polynomial samples. Okay, but without COT, we can use harness result from parity learning that shows at least exponential number is required for learning the correct parity. Okay, so we prove this theory result, but this seems all very abstract. So what does it really tell us about the experiments? Okay, so I think one key step in the proof is that is the sparsity in the attention. Okay, so in experiments, if we so here this is the sample complexity of learning different k, but not in a log plot. So we show that the sample complexity is actually just growing linear in k. Okay, and if we plot the learned attention from a trained transformer, we can see that the attention actually correctly attends to the secrets and it's sparse. Okay, so this suggests that the next token in the learned COT, the next token depends sparsely on previous tokens for a COT sequence, for a sequence with chain of thoughts. Okay, so this is the insights I want to highlight. So let me give give a more concrete example. So if you think about a sequence without COT that look like this, so then the final answer would depend on all the secrets. Okay, so if you have secrets k, then it would depend on k previous tokens. And learning such a distribution is hard statistically and computationally. Sorry, only statistically, not computationally. Okay. And however, if I have the chain of thought, then my final answer only depends sparsely on previous tokens. Okay, because the chain of thought already summarizes part of the computation results, so that the answer only needs to look at the previous chain of thought token. It doesn't have to look at the entire problem distribution. And therefore, this has a very sparse sequential dependence for the sequence distribution. And if we exploit this property or this assumption, then we can prove that transformer can learn with polynomial samples. Okay, so this
So
is yeah.
this means with the chain of thought in the inference and training time, your transformer when generating the answer or different parts of answer, paying attention to very few tokens in each step. That kind of means your chain of thought break down the complicated attention metrics and computing into simpler step, and each step is sparse. Am I right?
Yeah, exactly. So that's I think that's somehow corresponds to the long COT. It explains why we need long COT rather than just any COT.
I see. Thank you.
Yeah. Okay, so this was okay, so this was I think the main message we want to deliver from this project, and we also verify this. Sorry, so this project was finished before the R1, etc. Before the DeepSeek reasoning model. So at that time we still use Qwen, and we can see that the better performing model, for example, the Cuban mass on a mass data set would have in its solution would have sparser dependence on previous tokens. Okay, so here the y-axis is the entropy. So the higher the entropy, the denser the attention. Okay, so if you have a very sparse attention, then the entropy would be low. And we can see that the best model would have lower entropy and it tends only sparsely on previous tokens. Okay. Okay, so this is I think the conclusion for the second project. Okay, so basically we want to understand, so what is a learnable sequence for transformer? And our message is that, okay, a good sequence is a sequence that have sparse sequential dependence. Okay, so however, so this I think this doesn't answer our second question for language modeling, right? So our second question is, although the large language model are trained on corpus, on random web data set, but is tested on different benchmarks. So the distribution can be very different from the training data. So why does the model still generalize out of distribution? Okay, so this is our last part. Okay, we will talk about this third part. Okay, so for example, okay, so usually, so the training data would include the Wikipedia, for example. But if you look at one question, so I don't remember which data set this is, maybe Pika or something. It will ask something that is counterfactual. Okay, and so this is one would not. Okay, so I think that this is a personal belief. So I don't think this kind of question will show up in the pre-training. But there are also actually more statistical study that justify this by I think Professor Sanjeeva Arora. But etc. So I just want to give this example to show you the test data or test question can be very different from the training question. So why does the model still give the correct answer? Okay. And so in our project, we want to understand this question from the in-context learning perspective. Okay. So again, so I will just briefly talk about what is in-context learning. So in the GPT-3 paper, it's now we see that it's as an early paper, right? So when OpenAI still publish a lot of details, so they highlight in-context learning. Okay, so what is in-context learning? It gives you several demonstrating examples. Okay, this is as a prefix of the sequence, and they ask you to complete this sequence. Okay, so it tells you some examples. For example, this one is okay. I can permute the word so that you should learn from these examples to know that I want you to correct the order. Okay, so this one is doing the translation Okay, although I don't tell you directly what you should do, but you should infer that from the context. And I think the in-context learning is a good setup for understanding auto distribution because uh, this kind of thing, I mean, this exact format will not show up in the pre-training, right? It is clear that although it may require translation, but it doesn't have this particular format or these particular word combinations. Okay, so why does the models can still learn to follow this behavior and replicate this pattern? Okay, so this is our question. And so again, so I don't want to go too much into statistical learning analysis, but I want to highlight previous ideas. So I think one idea is to say that, okay, so a model can generalize to other distributions because other distributions have a shared representation. Okay. But I think this doesn't really apply to LLMs because we are not fine-tuning LLMs in new tasks. We just use the model directly, right? We are not saying, okay, we use the representation and we learn another classification layer. And another, I think, popular statistical learning uh, opinion is that, okay, we can learn a robust estimator that performs equally well on all distributions. Um, Again, I think this is not really describing LLMs because LLMs learn to adapt to the correct distribution. Okay, because if you have a robust estimator, it performs maybe suboptimally on all tasks, but LLMs can learn from the in-context examples and infer the correct behavior. Okay, so again, so how should we understand auto distribution from the in-context learning setup? Okay, so we go back to our so this is actually a follow-up project from the previous project. So we continue with the parity problem. Okay, so this is the parity. So S is a secret. The secret is a subset of indices. Okay, and so previously we didn't learn this in the in-context setup. And so what is the in-context setup? In-context setup was first fix a task S. Okay, a task S is a set of secrets. And how many tasks are there? We can see that it's exponentially in K. Okay, there are a lot of tasks uh, in total. And our question is, so can we train in context learning on a subset of tasks and generalize to unseen tasks? So basically out of these D to the K tasks, we just sample a random subset and then use the other ones to test our model. Okay. So what does that mean? So basically we input again we have two setups. Okay, so one is without COT, the other is with COT. And we input the model, we input into we input this sequence into the model where we have some demonstrative examples, and we ask the model to say, okay, can you infer the secrets from these examples and to output the correct solution? If the model were to do this, it basically needs to do some kind of Gaussian elimination to figure out the secret first and then output the result. Okay. And if with COT, then okay, so basically we augment the previous sequence with the intermediate computation and then ask, can they do this? Okay. Okay, so here I describe the data generation, but I just want to highlight that there's a hierarchy. So one is we sample some task. The other is within the task, we sample several sequences. Okay, a task is a set of indices which describes the secret. Okay, so given a secret, we can have many sequences, but we also need to determine what the secret is. Okay, so basically this is out of distribution because in the data generation, we pick a subset of tasks, but during the evaluation, we would evaluate the model on tasks that are not seen during the training. Okay, so if there's any question, please feel free to stop me. Okay, I think I have limited time, but the idea is, okay, as might be expected, the auto distribution would fail for sequences without COT, but would succeed for sequences with COT. Okay, this is expected, but so why does this really happen? Okay, so can we propose an explanation for this? And our explanation is that, um, okay, so before giving that explanation, so maybe I can give a quick question. So how many tasks would be required to solve all the D to the K tasks? So if you have any guess, maybe you can think about it. But I give you the result right away. So roughly the number of tasks, even though the total number of tasks is D to the K, but the number of tasks we need is only linear in D. Okay, we only need linear in D tasks in order to generalize to all the tasks with chain of thought. And so why does that happen? So we have a framework, a statistical learning framework for this, and we call this autoregressive composition. Okay, and it has a very complicated definition, but it doesn't matter. So the takeaway is that if a task can be considered a sequential composition of T tasks, where each task has K possibilities, then, sorry, I think I have this should not be K, this should be D. Okay. So if it's a sequence of T tasks where each task has D possibilities, then we only need D task in order to generalize to unseen, unseen tasks. Okay, we only need the number of tasks is only linear in D. Okay, so this is the theorem. Again, I think the theorem doesn't always matter, but why does this theorem explain what is going on for our observation? So if you think about this sequence without COT, then this output cannot be written as a composition of finite number of tasks because it's asked to output the result directly. Okay, and therefore, so for each secret, it corresponds to a different mapping, and therefore there are D choose K mappings in total, so that you would need D choose K tasks in order to solve this problem. However, if you have COT, then every digit output only depends on one digit, and this one digit has D choices because I have D digits in total, and therefore it's a composition of K tasks where each task has D choices, and therefore if fixing our framework our framework would say, okay, you only need D task, you only need D training tasks in order to generalize to all the unseen tasks. Okay, and so previous result was on parity. Again, we did some less synthetic experiments, and this is a translation where the model during training can learn to translate between pairs of languages, but it cannot see all the possible permutations. And we check whether the language can learn to do the translation between any sequential order of the translation. And again, we verify that the number of tasks required is linear in D. Okay, so I think that's everything that I want to talk about today. So we talk about 3 projects, and the takeaway for the first project is that to characterize generalization error for nonlinear models, we need to think about the data distribution. And for the second project, we want to say, okay, so a sequence is easy to learn for transformers if the sequence has sparse sequential dependence. And the third project is talking about out of distribution generalization. And the takeaway is that if the task or the distribution that we care about has sequential decomposability, then we can easily learn to generalize to out of distribution to unseen tasks. Okay, and thank you for your attention. And these are the references and the 3 works.
Great, thanks, Lin Zhao. It's a wonderful talk. And any questions from audience, you can either raise your hand by click the raise your hand button, or there is a Q&A tab. You can type in the question. And while the audience still preparing the question, I have a question. In the autoregressive compositionality theory or observation you are presenting, I personally have a guess, like if you look at the attention mechanism itself, somehow your in-context learning, the kind of serve as how to say a condition for your transformer to change its attention, change its behavior. As you mentioned, the chain of thought actually makes the attention matrix much more sparse than without chain of thought. Would that be possible if in the context learning setting, this sparse attention will be more easier, it will be easier to manipulate it by the content in the context, say switching from one attention to another attention because it's very sparse, than the very dense attention without chain of thought. Would that be one of the reasons why we observe this advantage of chain of thought?
Yeah, I think that's a very good comment. So our analysis, so the limitation of our analysis here is that they are all statistical. In other words, they are all information complexity. So we didn't really talk about, okay, so here can the transformer learn to implement this optimal algorithm? Okay. And therefore, so I think what you are suggesting is saying, okay, so so not only is informationally theoretical results, but you can also analyze the dynamics of transformer learning and show that it learns this. So based on the experiments, we think that's true, but we cannot do that analysis. It's too complicated. But I think my personal view is that I think that's correct.
Okay, yeah, great, thanks. So there are two questions in the chat, and one of the audience raised hand. So Jin Yu, I have allowed you to talk. Yeah, please. Okay.
Yeah, hi, Prof. Thank you for the wonderful talk. I think I have two questions. My first question is, does it mean that chain of thought is a necessary thing for in-context learning to work for the last part?
So here, I think it will be highly data dependent and task dependent, but for parity, it is. For this particular example, it is. So, but our message is that if you want the model to generalize to unseen tasks, to new distributions, then it needs some kind of decomposability in order to generalize.
Okay, I think my second question is, I think it's very interesting about this sparse attention that you showed when we do chain of thought. And it made me think of diffusion models, which also kind of improve performance when we sacrifice test time compute. So do you see like similarity with diffusion? Because with diffusion, there's a similar analogy to VAEs, right? VAEs generate blurry images, but then with diffusion, with sequential denoising, we are able to generate clearer images. So yeah, is it something related to that sparsity concept or like
Um, I think there could be, but I don't see how the sparse would translate. I think the common thing is so COT introduced more computation in the generation, and the diffusion also introduces more computation, right? Because I'm reusing my parameters multiple times. So I think that's common, but I don't really know what sparsity mean for diffusion.
okay, thank you so much.
There is one more question from Jay Zhang. It's in the Q&A tab. I believe, Jinzhao, if you click on the tab, you can see the second question.
Uh,
There's a Q&A
I
tab.
I guess I need to stop share. Sorry.
Yeah.
Okay, QA. Okay, I can see. Uh, yeah. So okay. So basically, I think so. So we are talking about learning from sequences. So in the language model literature, it will call the SFT, right? Supervised fine tuning. So the RL approach is saying, okay, so we don't have this guidance. So from the RL perspective, SFT is like expert iterations, right? Learning from experts. And but in the true RL would require the model to figure out the policy itself. So which is the RL, like GRPO in DeepSeek. And so basically, so I think that the common thing is we are showing that expert iteration or learning from expert is more efficient in the sample, but RL may have um, higher bars, right? So it can lead to better performance, but at the cost of competition, sorry, sample at the cost of sample complexity.
Yeah. There is one more audience raised hand. I think so. I saw someone with.
I don't think so.
Oh, go ahead.
Maybe it was still Jingyu, yeah. I could maybe ask one or two things.
Go ahead, please.
So you talked a lot about parity. Like, do you think would the conclusions be similar if you go a bit more complicated? Like, I guess multiplication would be a bit more complicated. Then you could go even more complex than that. Like, would you expect similar conclusions to hold?
Yeah, so in Berkeley, we tested arithmetic, and yes, it holds. But so we didn't. So making the proof work for arithmetic is much more complicated. So we didn't.
Okay, so
Yeah,
at least empirically, yeah. Okay.
yeah.
And I don't know how closely related it is, but and I don't really know the work, but I'm aware of a recent work from Wisconsin, like Dimitris Papalopoulos, on like self-improving transformers. I think they claim that they can train to multiply like small numbers and then have it like generate examples for gradually more digits and have it like self-improve. Are you aware of that work?
I'm not, but I know there are a lot of work that tries to do lens generalization, and
Okay.
usually
Like
the
in the
idea,
abstracts, they claim to go from 10 digit to 100-digit operations easily,
yeah.
but I don't know if there's any caveats or limitations. Yeah.
I don't know about that particular work, but
Yeah.
usually the most work require reformatting the data. So basically, I augment the position embedding, for example. That's the most popular way. So then they do not really fall in this next token prediction setup.
Okay.
So
Okay.
I'm
Well,
just talking about the vanilla version. Yeah, there are
okay.
other tricks.
I'll paste it in the chat in case you're interested, but yeah,
Oh, okay, thank
I'm
you.
not that familiar either. Yeah.
Okay, thank you. I'll take a look.
Okay. Any more audience questions? Okay. Otherwise, I guess we could wrap it up.
Okay, yeah. Thank you so much for everyone to attend the talk, and great thanks for Chinjiao to give us a nice talk. Thank you.
Thanks.
Okay, thank you for the invitation. Yeah, bye bye.